Hello friends, in this video I am going to discuss about restricted earth fault protection, which is also called as REF protection, which is used for implementation of earth fault protection in star connected windings of the transformer. Well, the need of REF protection is as such. If this is the winding configuration of our transformer, then in order to implement differential protection of the transformer, what we do, we introduce 3 CTs on the star side and we introduce 3 CTs on the delta side. Now through the connection of these CTs we implement differential protection, means if there is a fault in this region, these CTs are going to feed a fault to the 87 relay, that is the differential relay, and the relay will sense it as a fault, and it is going to give a trip signal to the circuit breaker. Now suppose if there is a fault in one of the phases, which is a single line to ground fault, then during this condition this fault current, that is this IF, might be so small that the differential relays might not pick up, means the fault current is so small that it is below the sensitivity of the differential relay and the differential relay might not pick up, and hence the fault remains undetected, which is not a desirable thing. So in order to avoid this situation, what we do, we implement REF protection, which is also called as the restricted earth fault protection. In that what happens, a protection system is designed which prevents or which provides protection for any fault in this region, which is an earth fault. If in this region there is any earth fault, like suppose there is an earth fault in this phase, then the REF relay is going to operate and it will give a tripping signal to the circuit breakers through REF protection. Now let us see the implementation of REF protection, like how the circuit is designed. So for that, let us just consider the star side of the transformer. So this is only the star side of the transformer, and for implementation of REF protection, what we do, we introduce 3 CTs in 3 phases, that is in each phase 1 CT is introduced and one more CT is introduced, that is in the neutral of the transformer, means 1 CT will be placed at this point. Now how the circuit will be designed, that all these 3 terminals along with the neutral terminal of the REF relay will be joined, and again this terminal will be joined with these 3 terminals, and in between these two wires a relay will be introduced, means a relay coil is introduced at this point, and this relay is numbered as 64 REF, or just an REF relay. Now how this relay is going to operate, or the purpose of this relay, is that it is going to protect the transformer against any fault in between the zone of these CTs. Means if there is a fault at this point, then this relay is going to operate, or if there is a fault at this point or at this point, then this relay is going to operate, or if there is a fault at this point, then in this case the fault current might be so small that the differential relay might not pick up, and hence during that condition the REF relay should operate. Now this relay, that is the REF relay, should not operate if there is fault outside the zone of the CTs. Means if there is a fault here, then this relay should not operate. Let us see how it happens. If there is a fault at this point, then the fault current will be fed in this direction. It will take up this path, and again through the neutral it will return back. It is going to return and it will flow in this direction. So hence, in order to balance this current, a current should flow in the neutral CT, which will be in this direction. It will take up this path, it will take up this path. And in order to balance the current in this phase, the current should flow in the CT in this direction. Now it is going to take up this path, and again at this point we can see that these two current, that is this current and this current, they are opposite to each other, and hence the current flowing in this coil will be I is equal to 0, and hence it is not going to pick up. Means the relay will remain stable and the transformer will remain stable, because it is not a fault in the zone of the transformer, or it is not a fault in the transformer, it is fault somewhere outside the zone of the transformer. Now what about the operation of the relay when there is a fault internal to the zone of the transformer? Means if there is a fault at this point, then let us see how the relay is going to operate. Suppose there is a fault in this phase, that is the third phase, and it is an earth fault here, and then the current would take up this path, and through the fault point it will flow through the neutral, and again it will take up this path. So in order to balance this current, the current in the neutral should flow in this direction, it will flow in this direction, and the current from the CT side, means from this side also the current will be fed if there is a source in this side. Then in order to balance this current, the current should flow in this direction and it will take up this path, and at this node both these two currents are getting added up and the current will flow in this direction. It will take up this path. Now there is a flow of current in this REF relay, and hence the relay is going to sense it as a fault, and which is a fault in the zone of the transformer. Hence it is going to send a tripping signal to the circuit breaker because it is an internal fault or fault internal to the transformer. So the transformer should be isolated from the system. Now one thing while designing this scheme is also called as the high impedance REF, that is high impedance REF. Well, later on in this video we shall see why this is called as high impedance REF. We shall keep in mind that the CT ratio, that is the CT ratio of this phase and this phase, and along with this CT, they should have same CT ratio. Like we cannot have different CT ratios. Well, in low impedance REF protection, that is the REF protection, low impedance REF protection, which is implemented through numerical relays, there is no such necessity that the CT ratios should be same. Like we can have these three CT ratios having a same CT ratio, and this CT ratio can be different from these three CTs. So this thing is possible only through low impedance REF protection, which is implemented through numerical relays. And for high impedance REF protection, the CT ratios of all the CTs should be same. Now let us see why we are calling this circuit as high impedance REF protection. So as we saw, this was the basic scheme of implementation of REF protection. Now suppose there is a heavy fault at this point. So it's obvious that the fault is outside the zone of the CTs, so this REF relay should not operate because the current would take up this path, and it would flow through the CT, and we can see that both these currents, that is the current that is coming here and the current coming here, they are equal and opposite, and hence the relay coil is not getting any current. Now suppose that this fault current was so high that this CT got saturated, means saturation occurred in this CT, the CT got saturated. So now it is assumed that when the CT got saturated, this current got zero, means this current became zero. Now I is equal to 0, hence this current has no value. Now the only current which is flowing in the circuit is the current through the neutral CT, and since this current is flowing, and now this current will flow, and this current is not facing any opposition from the phase side CT, so what will happen? Ultimately it will take up this path, and this REF relay is sensing a current, means now a current is flowing in this REF relay, and the relay will treat an external fault as a fault in the transformer, and it is going to issue a trip signal to the transformer, which is not desirable because the relay should remain stable when there is a fault outside the range of outside the zone of the CTs. Now in order to avoid such situation, what we do some modification in the circuit. Now the modification is as such that apart from introducing a relay, that is the 64 relay, we also introduce a high resistance in this circuit, and this resistance is called as stabilizing resistance. Now suppose there is a fault and this CT got saturated. Now the fault current will flow, and there will not be any reflection of this current in the CT, so current flowing here will be I is equal to 0, and the only current which will flow in the circuit is this current. Now this current is taking up this path. Now since the resistance is so high that this current cannot take up this path, this current will not be able to take up this path, and the current would flow in this way, and it will take up this CT path, and it will keep on rotating in the circuit, and it will not flow through the relay coil. Well, about the value of this stabilizing resistance, means how much should be the value of this stabilizing resistance, we shall see in some other video. Means what is the basis of calculation of this stabilizing resistance, that the REF relay should not operate when there is a fault external to the zone of operation. Now apart from this REF relay, there are certain places that we introduce one more relay at this point, and this relay is called as SEF relay, also called as standby or fault relay. which is used to provide protection against the persisting faults in the system. So this was all about the REF protection of the transformers. Well, in the next video we shall see about the calculation of the stabilizing resistance needed for high impedance REF protection.